Hello, in this lecture we'll answer two questions. In the first question, we find out the length of line segment X that is equal to DE, and in the second question, we will find out the value of the shaded area that is inside this quarter circle. Okay, so in the first question, we have in the drawing triangle ABC. This angle ABC equals to 30 degrees. This angle ACB equals to also 30 degrees. And this angle DAE equals to 60 degrees. Line segment PD equals to 5 units. Line segment EC equals to 4 units. And our mission is to find out the length of line segment DE that is equal to X. Okay, so first of all, we'll focus on triangle ABC. In triangle ABC, we have those two angles that are equal to each other. They are both equal to 30 degrees. So I'll write it down. In triangle ABC, this angle ABC equals to this angle that is actually angle ACB. And both angles are equal to 30 degrees, therefore they are equal to each other. I repeat again, in triangle ABC, angle ABC equals to angle ACB, they are both equal to 30 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. Side AB is located in front of this angle, side AC is located in front of this angle, therefore those two sides must be also equal to each other. Okay? From the fact that those two angles are equal to each other in triangle ABC, we will conclude that side AB equals to side AC. According to the rule that I mentioned, here side AB, this side is equal to this side, that is actually side AC. We define angle BAD as alpha. We define angle EAC as beta. And we know that the sum of the angles in any triangle, and especially in triangle ABC, must be equal to 180 degrees. Okay? So actually, which angles we have triangle ABC? We have this angle that is equal to 30 degrees, plus this angle that is also equal to 30 degrees, plus this angle that is equal to alpha according to our definition, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta according to our definition. In total, the sum of those all angles must be equal to 180 degrees according to the rule that the sum of the angles in a triangle is equal to 180 degrees. So the sum of those angles must be equal to 180 degrees. So here we have 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is equal to 120 degrees, plus alpha plus beta is equal to 180 degrees. So here we subtract 120 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 120 degrees, it is equal to 60 degrees. So we actually found out that alpha plus beta equals to 60 degrees. In the next step, we'll do two constructions. The first construction is that from point A, we will draw a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. Okay. For this angle equals to alpha according to our construction. And the second construction that we will do is from point C, we will draw a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. So this angle equals to 30 degrees according to our construction. In the next step, we will extend the two straight lines until they intersect with each other. And we will define the intersection point between the two extended straight lines as point F. So here we create a triangle AFC. So in the next step, we prove that this triangle AFC is congruent to this triangle ABD. Okay, we prove that this triangle ABD is congruent to this triangle AFC. So why those two triangles congruent to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. Okay, so this angle, this is actually angle BAD. Is equal to this angle, that is actually angle CAF. And both angles are equal to alpha, therefore they are equal to each other. I'll repeat again. Angle BAD and triangle BAD equals to angle CAF and triangle CAF. They are both equal to alpha, therefore they are equal to each other. In addition, we have already found out that AB equals to AC. So side AB in triangle ABD is equal to side AC in triangle AFC. Okay, repeat again. AB equals to AC. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So this angle, it is actually angle ABD in triangle ABD is equal to this angle that is actually angle ACF. They are both equal to 30 degrees, therefore they are equal to each other. Repeat again. Angle ABD in triangle ABD is equal to angle ACF in triangle ACF. They are both equal to 30 degrees, therefore they are equal to each other. So we actually prove that the triangle ABD is congruent. This is the sign of congruent for triangle AFC. According to angle side angle rule. Repeat again, I proved actually the triangle ABD is congruent to triangle AFC according to angle side angle rule. I will explain what I mean here. We have those two angles and the side that attach to those two angles, and the side AB, are corresponding congruent to those two angles and the side that attach to those two angles, that is side AC in triangle AFC. Therefore, those two triangles are congruent to each other according to angle side angle rule. We have two angles in the side that attach to those two angles in triangle ABD that are corresponding congruent to those two angles and the side that attach to those two angles in triangle AFC. Therefore, those two triangles congruent to each other according to angle side angle rule. And from the fact that those two triangles congruent to each other, we conclude two things. The first thing that we will conclude is that side BD in triangle ABD is equal to side FC in triangle AFC. Okay. Side BD in triangle ABD is equal to side FC in triangle AFC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say BD and FC, will be equal to each other. Okay, BD equals to FC, but it is given us the question that side BD equals to 5 units. So you can write here that BD equals to 5 units. And from this equation, 5 equals to BD equals to FC. We derive that side FC is also equals to 5 units. Side FC equals to 5 units. And the second thing that we conclude from the fact that those two triangles congruent to each other is that side AD equals to side AF. Side AD in triangle ABD is equal to side AF in triangle AFC. According to the same rule that the corresponding sides in congruent triangles are equal to each other. So if we define side AD as A, side AD equals to A according to our definition, here AD equals to A, then from this equation A equals to AD equals to AF, we will derive that side AF is also equals to A. AF equals to A. Okay, here side AF is also equals to A. In the next step, we will join points E and F together by a straight line. and we will prove that the green triangle, triangle ADE, this triangle is congruent to the orange triangle, triangle AEF. But before that, we have already found out that alpha plus beta equals to 60 degrees. So here, this angle, angle FAE, that is equal to alpha plus beta, equals to 60 degrees, according to what we have already found out. This angle equals to 60 degrees. Okay, so why those two triangles can go into each other? So we prove that the green triangle, triangle ADE, this triangle, is congruent to the orange triangle, triangle AEF. So why those two triangles can go into each other? First of all, we just right now found out that side AD in the green triangle is equal to side AF. Okay, so side AD in the green triangle is equal to side AF in the orange triangle, and they are both equal to A, therefore they are equal to each other. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So angle DAE in the green triangle is equal to angle EAF in the orange triangle. And they are both equal to 60 degrees, therefore they are equal to each other. Repeat again, angle DAE equals to angle EAF. They are both equal to 60 degrees, therefore they are equal to each other. And finally, we have side AE, that is a common side that belongs to both triangles. So side AE equals to itself. AE equals to AE. It's a common side that belongs to both triangles. Repeat again. Side AE equals to side AE. It's a common side that belongs to both triangles. So we actually proved that the green triangle, triangle ADE, is congruent to the orange triangle, triangle AEF, according to side angle side rule. The green triangle, triangle ADE, is congruent to the orange triangle, triangle AEF, according to side angle side rule. I'll explain what I mean. Here we prove that those two sides and the angle that is included between those two sides in the green triangle are corresponding congruent to those two sides and the angle that is included between those two sides in the orange triangle. Therefore, we proved that those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we conclude that side DE equals to side EF. side DE equals to side EF according to the rule that corresponding sides congruent triangles and congruent triangles are equal to each other. But according to what is given as the question, side D equals to x. So you can write down the D equals to x, and from this equation x equals to D equals to EF, we derive that side EF is also equals to x. Okay, side EF is also equals to x. Here EF equals to x. So in the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle EFC. Okay. So, what is the law of cosines? The law of cosines is true in any triangle. I've already mentioned the law of cosines a couple of times in the previous lectures, so I'll do it quickly. The law of cosines is true in any triangle, so I write down in any triangle. So if we have triangle ABC that could be any triangle, this is triangle ABC. And we know that the length of side AB is A units, side AC equals to B units in its length, and the angle between side AB and side AC is theta, and side BC equals to C units in its length. Then, according to the law of cosines, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Repeat again, in this triangle, triangle ABC that could be any triangle, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay, so we'll implement the law of cosines in this triangle, triangle EFC. Therefore, I will copy triangle EFC in this page, and we'll implement the law of cosines in triangle EFC. Angle FCE, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. So this is triangle EFC with the curvature of the original drawing. Now we will implement the Pythagoras theorem in this triangle, triangle EFC. Here, by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here we will implement the mistake. We'll implement the law of cosines in this triangle EFC. Okay, so here I write down according to the law of cosines. We will implement the law of cosines in this triangle EFC. According to the law of cosines, we get here that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. This equation is the implementation of the law of cosines in this triangle EFC. Okay, here x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So x squared equals to 4 squared is 16 plus 5 squared is 25 minus 2 times 4 is minus 8 and minus 8 times 5 is minus 40 and cosine 60 degrees equals to 1/2, so we substitute cosine 60 degrees by 1/2. So in total this expression equals to minus 40 over 2. So actually found out that x squared equals to 16 plus 25 is 41 and minus 40 over 2 is minus 20. So x squared equals to 41 minus 20, so that is to say x squared equals to 41 minus 20 is 21. 41 minus 20 is 21, so x squared equals to 21. Here we take a root out of this equation and we get that x equals to the positive square root of 21 units, so in terms of numbers it is equal to 4.58 units. Okay, and the reason that x equals to the positive square root of 21 is because of the fact that x is a length, and as x is a length, it must be a positive number. So here the answer to the question is that x equals to either the positive square root of 21, or in terms of numbers it is equal to 4.58 units. Okay, x that is equal to dE equals to x, it is equal to either the positive square root of 21, or in terms of numbers it is equal to 4.58 units. We finished with the first question. In the next step I will present to you the second question. In the drawing we have a quarter circle. Inside this quarter circle we have a circle and the semicircle that are tangent to each other at this point, and we also know that this circle is tangent to the quarter circle at this point, and on the eye of both the circle and the semicircle is equal to 2 units. And our mission is to find out the value of the shaded area. So first of all, because of the fact that this is a quarter circle, this point must be the center of the quarter circle. So we define this point as point O. As I've already mentioned, point O is the center of the quarter circle. Point O is the center of the quarter circle. And this angle is equal to 90 degrees. It is true in any quarter circle. This angle must be equal to 90 degrees. We'll define this point as point A. We'll define this point as point B. Here, AO and OB, they are both the radii of the quarter circle. So here, AO and OB, they are both the radii of the quarter circle. So we'll define the radius of the quarter circle as capital R, therefore AO equals to capital R according to our definition, and OB also equals to capital R according to our definition. Okay? And we have here the radius OB is tangent to this circle at this point. We define the point of tendency as point M. So here M is the point of tendency of tangent OB, that is also the radius of the quarter circle, of tangent OB with this circle. We will define the center of this circle as point P, and we will define the center of the semicircle as point Q. Okay? Here, point P is the center of the circle. Point M is the point of the circle itself. Therefore, PM is the radius of the circle that is equal to 2 units. Okay? And we also have rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have tangent AB that is tangent to this circle as point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is drawn to the point of tendency. That is to say, the radius OM it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule number 1. Actually, you can implement rule number 1 in our drawing, because in our drawing we have the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent OB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MP. So if OB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1, of course. In the next step, from the center of this circle that is actually point P, we will draw perpendicular on QO. Okay, so here actually this angle equals to 90 degrees according to our construction, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and QO as L. L is the touching point of the perpendicular from point P and QO. Actually, by this construction, we created here quadrilateral LPOM that has 1, 2, 3 right angles. Repeat again. Inside quadrilateral LPOM, we have 1, 2, 3 right angles. So I write it down. Inside quadrilateral LPOM, we have 3 right angles, and the sum of 3 right angles is 90 degrees times 3 is 270 degrees, plus the size of the fourth angle that is actually angle LPM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we subtract 270 degrees from this equation, and we will get that the missing angle LPM, is equal to 360 degrees minus 270 degrees, it is equal to 90 degrees, it is a right angle. Okay, so we can write here that this angle LPM, it is a right angle, is equal to 90 degrees. So actually we found out that inside quadrilateral LPOM, all of its angles inside it are right angles. Inside quadrilateral LPOM, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral LPOM that has 4 right angles as a rectangle. So I write it down, quadrilateral LPOM is a rectangle. Okay. Quadrilateral LPOM is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle LPOM, its opposite sides are equal to each other. It means that PM equals to LO. PM equals to LO, according to the rule that the opposite sides of a rectangle are equal to each other. Okay? But we know that PM equals to 2 units, so we can write here that PM equals to 2 units. And from this equation, 2 equals to PM equals to LO, we will derive that LO is also equals to 2 units. Here, LO is also equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that side LP equals to side OM. LP equals to OM. LP equals to OM according to the same rule. So if we define side LP as X, here LP equals to X according to our definition. Side LP equals to X. Then from this equation, X equals to LP equals to OM, we conclude that side OM is also equals to X. Side OM is also equals to X. In the next step, we'll focus at this point, that is the touching point of the circle and the quarter circle. And we will define the touching point between the quarter and the quarter circle, and we will define the touching point between the circle and the quarter circle as point K. Repeat again, point K is the touching point between this circle and the quarter circle. Actually, at point K, they have an internal notch between them. That is to say, they are touching each other internally at point K. And whenever you have two circular shapes that have an internal notch between them, then the straight line that joins their centers together must pass through their touching point. In this case, their touching point is point K. I repeat again, whenever you have two circular shapes that have an internal notch between them, then the straight line that joins their centers together must pass through their touching point. In this case, it's point K. So here, point O is the center of the quarter circle. Point P is the center of the circle. And the straight line that connects the two centers together is straight line OP. Okay? And according to the rule that I mentioned, this straight line OP, must pass through their touching point, that is actually point K. So the straight line OP passes through point K. Okay? The straight line OP passes through point K, that is their touching point. That is to say, OPK is one straight line. So you can write down that OPK, line segment OPK, is one straight line. Line segment OPK is one straight line, or we can also say, in other words, that points O, P, and K, they are all located on the same straight line. Okay, so if OPK is a straight line, then OK is also a straight line. OK is also a straight line. What is the definition of the straight line OK? Point O is the center of the quarter circle. Point K is the point on the quarter circle itself. This is exactly the definition of a radius. That is to say, OK is the radius of this quarter circle that is equal to capital R according to our definition. Therefore, OK equals to capital R, that is the radius of the quarter circle. Okay? So here, point P is the center of the circle. Point K is the point on the circle itself. So PK is the radius of this circle that is equal to 2 units according to what is given as the question. So here PK equals to 2, so we can write here that PK equals to 2. So in conclusion, we found out that OK equals to R and PK equals to 2. And what is the length of line segment PO? The length, it is very easy to see from the drawing that the length of line segment PO is equal to OK minus PK. Again, OK minus PK equals to OP. OP equals to OK minus PK. Repeat again. OP equals to OK minus PK. So OP equals to OK. OK equals to capital R, that is the radius of the quarter circle. So we substitute OK by capital R minus PK. PK equals to 2 units, it is the radius of the circle. So in conclusion, we found out that OP equals to capital R minus 2. Here OP equals to capital R minus 2. Okay. Now I will copy the right triangle OPM in a new page, and we implement the Pythagoras theorem on this triangle OPM. Okay. So the hypotenuse OP equals to capital R minus 2. OP equals to capital R minus 2. OM equals to X. And PM is the radius of the circle that is equal to 2 units. So I copied the right triangle OPM in this new page. Next step, we will implement the Pythagoras theorem on this right triangle OPM. So here, by PT is the progression for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse is OP, therefore the square of the hypotenuse is OP squared. It must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to PM squared plus OM squared. So here the hypotenuse OP equals to capital R minus 2, therefore OP squared equals to capital R minus 2 squared, and it is equal to PM squared. PM equals to 2, so PM squared is 2 squared, that is 4, plus OM squared. OM equals to X, therefore OM squared equals to X squared. So in conclusion, we found out that according to equation number 1, R minus 2 squared equals to 4 plus X squared. Here we will open the brackets on this side of equation number 1, and we get that according to equation number 1, R minus 2 squared equals to R squared, plus 2 squared, that is 4, minus 2 times R times 2, that is minus 4R, and it is equal to 4 plus X squared. Here we have 4 on both sides of the equation, so 4 will get cancelled. So what is left from equation number 1 after we cancel 4? What is left here is that in this side we have X squared, in the other side we have R squared minus 4R. So in conclusion, we actually found out that according to equation number 1, X squared equals to R squared minus 4R. Okay. In the next step, we'll focus at this point, that is the touching point between the semicircle and the circle. And we'll define this touching point as point T. Point T is the touching point between the semicircle and the circle. Actually, at point T, the circle and the semicircle have an external length between them. That is to say, at point T, they are touching each other externally. Or they are touching each other externally at point T. And whenever you have two circular shapes that have an external length between them, then the straight line that joins their centers together must pass through their touching point. I'll repeat again, whenever you have an internal length between two circular shapes, then the straight line that joins their centers together must pass through their touching point. In this case, it's point T. So here, point P is the center of the circle. Point Q is the center of the quarter circle. And the straight line that joins their centers together is QP. So the straight line QP, according to the rule that I mentioned, must pass through their touching point, that is point T. Okay? So the straight line QP must pass through point T. The straight line QP must pass for point T, that is to say QTP is one straight line. Okay, so QTP is one straight line. Line segment QTP is one straight line. We can also say that points Q, T, and P, they are all located on the same straight line. Okay, it is exactly like saying that QTP is one straight line. So here, if QTP is a straight line, then QP is also a straight line. QP is a straight line. So we know that QP is a straight line, and what is the length of the straight line QP? The length of the straight line QP from the drawings is very easy to see that QP equals to QT plus TP. QT plus TP. Repeat again that the length of the straight line QP equals to QT plus TP. So here point Q is the center of the semicircle. Point T is the point of the semicircle itself. That is to say QT is the radius of this semicircle that is equal to 2 units. Likewise, point P is the center of the circle. Point T is the point of the circle itself. That is to say, PT is the radius of this circle that is also equals to 2 units. So in conclusion, found out that QT equals to 2 and TP also equals to 2. So here QP equals to QT that is 2 plus TP that is also 2. So in conclusion, we found out that QP equals to 2 plus 2, that is 4. Okay, so we found out that the straight line QP equals to 4 units in its length. Here we can write down that QP, the straight line QP equals to 4 units. Okay. And what is the length of line segment QA? Point Q is the center of the semicircle. Point A is the point on the semicircle itself. Therefore, QA is the radius of this semicircle that is equal to 2 units. And what is the length of line segment QL? The length of line segment QL, it is very easy to see from the drawing that the length of line segment QL, it is equal to here QL equals to AO, that is the radius of the quarter circle, minus AQ minus LO. Repeat again, the length of line segment QL equals to AO, that is the radius of the quarter circle that is equal to capital R, minus AQ, that is the radius of the semicircle that is equal to 2, minus LO, that is equal to 2 units. So in conclusion, we found out that QL equals to capital R minus 2 minus 2 minus 2 minus 2 is minus 4. So in conclusion, we found out that QL equals to capital R minus 4. Here QL equals to capital R minus 4. So in the next step, I'll copy the right triangle QLP in a new page, and we will implement the Pythagoras theorem on this right triangle QLP. Okay. QL equals to capital R minus 4. and the hypotenuse LP equals to 4 units, and LP equals to x. So this is the right triangle QLP that I copied from the original drawing. We will implement the Pythagoras theorem in this triangle QLP. So here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is QP, therefore the square of the hypotenuse is QP square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to QL square plus LP square. Okay. QP equals to 4, therefore QP square is 4 squared, that is 16. And it is equal to QL square. QL equals to capital R minus 4, therefore QL square will be equal to capital R minus 4 square plus LP square. LP equals to x, so LP square is x square. So in conclusion, found out that according to equation number 2, 16 equals to capital R minus 4 square plus x square. Here we will open the brackets on this side of the equation number 2, and we get that according to equation number 2, 16 equals to capital R minus 4 is capital R minus 4 square is capital R square plus 4 square, that is 16, minus 2 times capital R times 4 is minus 8R plus x squared. Okay, so here we have 16 on both sides of the equation, so 16 will get cancelled. So what is left from equation number 2 after we cancel 16? On this side of the equation nothing is left, so we have 0, that is equals to R squared minus 8R plus x squared. So here we will add 8R to this equation, equation number 2, and we'll get that according to equation number 2, R equals to R squared, 8R minus 8R is 0, so 8R equals to R squared plus x squared. Here we will subtract R squared from this equation, equation number 2, and we get that according to equation number 2, x squared equals to 8R minus R squared. So according to equation number 2, we found out that x squared equals to 8R minus R squared, while according to equation number 1, we have already found out that x squared equals to R squared minus 4R. So actually we have two different expressions for x squared. Therefore, we will create the third equation that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. Okay? So x squared according to equation number 1 equals to R squared minus 4R. It must be equal to x squared according to equation number 2, that is 8R minus R squared. So we found out that according to equation number 3, R squared minus 4R equals to 8R minus R squared. Here we add R squared to this equation, equation number 3, and we get that according to equation number 3, r squared plus r squared is 2r squared minus 4r, that is equal to 8r. So here we will add 4r to this equation, equation number 3, and we will get that according to equation number 3, 2r squared, 4r minus 4r is 0, and 8r plus 4r is 12r. So we found out that according to equation number 3, 2r squared equals to 12r. Here we will divide this equation, equation number 3 by 2, and we get that according to equation number 3, 2r squared over 2 is r squared, and it is equal to 12r over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we subtract 6r from this equation, equation number 3, and we will get that according to equation number 3, r squared minus 6r equals to 0. Okay, so here we will take r as a common factor from these two expressions. So r is a common factor. What is left from r squared after we took from it r as a common factor? What is left is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left is actually minus 6. So in conclusion, we found out that r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. The first solution is that r equals to 0. But because of the fact that r is the length of the radius of the quarter circle, r as a length, it must be a positive number, it can never be equal to 0. So we cancel this solution, and we left only with the second solution, that r minus 6 equals to 0. Here we will add 6 to this equation, and we will get that r, that is the radius of the quarter circle, it is equal to 6 units. So now we know that the radius of the quarter circle equals to 6 units, and we know that the area of any quarter circle equals to the area of the circle over 4, and the area of the circle is pi r squared, and r equals to 6, and if we divide the area of the circle by 4, we get the area of the quarter circle, that is to say the area of the quarter circle will be equal to pi r squared over 4 when r equals to 6 units. And what is the value of this shaded area? The value of the shaded area in the drawing it is equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I'll repeat again. The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Okay? So we have already found out that the area of the quarter circle equals to pi r squared over 4, and r equals to 6. Minus the area of the circle equals to pi r squared, and r equals to 2, so it is pi 2 squared. Minus the area of the semicircle, that is equal to the area of the circle over 2, and the area of the circle is pi r squared, and r equals to 2. Therefore, the area of the semicircle will be equal to pi 2 squared over 2. So in conclusion, we found out that the value of the shaded area equals to this expression. R equals to 6, therefore R squared is 6 squared, that is 36. So in total, this expression equals to 36 pi over 4, that is the area of the quarter circle, minus the area of the circle, that is pi r square, pi 2 square. 2 square is 4, and 4 times pi is 4 pi. 4 pi is the area of the circle, minus the area of the semicircle, that is pi 2 square over 4. 2 square is 4, 4 over 2 is 2, and 2 times pi is 2 pi. So the area of the semicircle is 2 pi. And it is equal to, here 36 over 4 is 9, and 9 times pi is 9 pi. So in total, this expression equals to 9 pi, that is the area of the quarter circle, minus 4 pi, that is the area of the circle, minus 2 pi, that is the area of the semicircle. So here 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area is equal to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, so here I'll repeat again. The value of this shaded area, it is equal to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. We finished with the second question. In the next step, I will summarize the lecture. We'll start with the first question. In the drawing, we have triangle ABC. You know that angle ABC equals to 30 degrees, angle ACB also equals to 30 degrees, angle DAE equals to 60 degrees, side BD equals to 5 units, side EC equals to 4 units, and our mission is to find out the value of side DE, or line segment DE, that is equal to X. So first of all, we focused on the right triangle, triangle ABC. The right triangle, in triangle ABC. In triangle ABC, you know that those two angles, they are equal to each other, they are both equal to 30 degrees, therefore they are equal to each other. So in triangle ABC, we know that angle ABC equals to angle ACB, and they are both equal to 30 degrees, therefore they are equal to each other. And according to the rule that in front of equal angles in the triangle, there are equal sides, we get that side AB is equal to side AC. Why? Because they are located in front of those two equal angles. Therefore, AB equals to AC. We defined angle BAD as alpha and angle EAC as beta. And we know that the sum of the angles in triangle ABC, in any triangle, and especially in triangle ABC, must be equal to 180 degrees. So which angles we have inside triangle ABC? We have this angle that is equal to 30 degrees, plus this angle that is also equal to 30 degrees, plus this angle that is equal to alpha, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta. In total, the sum of those all angles must be equal to 180 degrees. Okay, so here 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 180 degrees, 120 degrees. So in this side of the equation, we have 120 degrees plus alpha plus beta, that is equal to 180 degrees. We subtracted 120 degrees from this equation and found out that alpha plus beta equals to 180 degrees minus 120 degrees equals to 60 degrees. So in conclusion, we found out that alpha plus beta equals to 60 degrees. Then we did two constructions. The first construction is that from point A we do a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. So this angle equals to alpha according to our construction. And the second construction that we did is that from point C we draw a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. Again, this angle equals to 30 degrees according to our construction. Then we extended the two straight lines until they intersect with each other at point F. Point F is the intersection point of those two straight lines. So actually in this way we created triangle AFC, and we proved that triangle AFC is congruent to this triangle, triangle ABD. So why those two triangles congruent to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. I'll repeat again. Angle BAD equals to angle CAF equals to alpha. In addition, we have already proved that side AB equals to side AC. Here, side AB equals to side AC. So here, side AB of triangle ABD equals to side AC of triangle AFC. And finally, those two angles are both equal to 30 degrees, therefore they are equal to each other. I'll repeat again. Angle ABD equals to angle ACF equals to 30 degrees. So we actually proved that triangle ABD, this triangle, is congruent to this triangle, triangle AFC, according to angle side angle rule. I'll explain what I mean. We have those two angles and the side that attached to those two angles in triangle ABD are corresponding equal to those two angles and the side that attached to those two angles in triangle AFC. Therefore, those two triangles can join to each other according to angle side angle rule. And from the fact that those two triangles can join to each other, we will conclude two things. The first thing that we will conclude is that side BD equals to side FC. Here, side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given as the equation, side BD equals to 5. So we can write down here that side BD equals to 5. So from this equation, 5 equals to BD equals to FC, we will derive that FC is also equals to 5 units. Here, FC equals to 5 units. And the second thing that we will conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. Side AD in triangle ABD is equal to side AF in triangle AFC. I repeat again, side AD equals to side AF equals to side AD. Side AD equals to side AF. So if we define side AD as A, yeah, side AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we will derive that AF is also equals to A. Here, AF equals to A. In the next step, we join points E and F together by a straight line, and we proved that the green triangles can go into the orange triangle. Why those two triangles can go into each other? First of all, we have already found out that alpha plus beta equals to 60 degrees, therefore this angle, that is alpha plus beta, must be equal to 60 degrees. So why the green triangle is congruent to the orange triangle? First of all, we just right now proved that side AD equals to side AF. Here, side AD equals to side AF, and they're both equal to A, therefore they're equal to each other. In addition, we found out those two angles are both equal to 60 degrees, therefore they are equal to each other. Here, angle DAE equals to angle EAF equals to 60 degrees. And finally, we have side AE, that is a common side, it belongs to both triangles, so side A equals to itself, A equals to itself, it's a common side that belongs to both triangles. So we actually proved that the green triangle is congruent to the orange triangle according to side angle side rule. Those two sides and the angle that is included between those two sides in the green triangle is corresponding congruent to those two sides and the angle that is included between those two sides in the orange triangle. Therefore, those two triangles congruent to each other according to side angle side rule. And from the fact that those two triangles congruent to each other, we will derive that side DE equals to side EF. Side DE equals to side EF according to the rule that corresponding sides in congruent triangles are equal to each other. But according to what is given as the equation, side DE equals to x. So we can write here that D equals to x, and from this equation x equals to D equals to EF, we will derive that side EF is also equals to x. Okay? In the next step, I presented to you the law of cosines, and we implemented the law of cosines in this triangle, triangle EFC. So what is the law of cosines? The law of cosines is true in any triangle. So here we have triangle ABC that could be any triangle. The length of side AB is A units. The length of side AC equals to B units. And the angle between side AB and side AC is theta. And the length of side BC is units. Then in this triangle ABC that could be any triangle, the following equation is true. That C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Then we implemented the law of cosines in this triangle EFC. This is triangle EFC that I copied from the original drawing. Here, this angle ECF FCE equals to 30 degrees plus 30 degrees, that is 60 degrees. Side EF equals to x, side EC equals to 5 units, and side EC equals to 4 units. So in this triangle EFC, according to the law of cosines, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Okay, so here x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40. Cosine 60 degrees equals to 1 half, so in conclusion, found out that this expression equals to minus 40 times 1 half. Okay? So here we have x squared, that is equals to 16 plus 25 is 41. And minus 40 over 2 is minus 20. So in conclusion, found out that x squared equals to 41 minus 2. 41 minus 20. So x squared equals to 41 minus 20 is 21. So we found out that x squared equals to 21. And we took a root out of this equation and found out that ax equals to the positive square root of 21, or in terms of numbers, it is equal to 4.58, and the reason that x equals to the positive root only because of the fact that x is a length, x is a length, and as a length, it must be a positive number. So the answer to the question is that here, the length of line segment DE that is equal to x, it is equal to either to the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. We finished with the first question, then I presented to you the second question. So here in the drawing, we have a quarter circle. Inside this quarter circle, we have a circle and a semicircle, and they are tangent to each other at point T, and the circle is tangent to the semicircle at the quarter circle at point K. Again, the circle is tangent to the quarter circle at point K, and we know that the radii of both the circle and the semicircle is equal to 2 units. And our mission is to find out the value of the shaded area. So first of all, because of the fact that this is a quarter circle, it means that this point O is the center of the quarter circle. Angle LOM, this angle equals to 90 degrees, and OB and AO are both the radii of this quarter circle. So we define the radius of the quarter circle as capital R. And here we have the radius OB is tangent to the circle at point M. Point M is the point of tendency of tangent OB with this circle. And here point P is the center of the circle, point M is the point of the circle itself, therefore PM is the radius of this circle. And we have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So tangent AB is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to the point of tendency. That is to say, the radius OM, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to this rule, rule number 1. Actually, we can implement rule number 1 in our drawing, because in our drawing we have the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent OB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MP. So if OB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. Then from the center of this circle, that is to say from point P, we draw perpendicular on QO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. And we defined the touching point of the perpendicular from point P and QO as L. L is the touching point of the perpendicular from point P and QO. So actually, by doing this construction, we created quadrilateral LPOM that has 1, 2, 3 right angles. So, and the sum of 3 right angles is 90 degrees times 3 is 270 degrees, plus the size of the fourth angle, that is angle LPM. In total, the sum of those all 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation, and we found out that the missing angle LPM equals to 360 degrees minus 270 degrees, it is 90 degrees. So we found out that the fourth angle is equal to 90 degrees. So actually we found out that all the angles inside quadrilateral LPOM are right angles. That is to say, quadrilateral LPOM has 4 right angles. And then the quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral LPOM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LPOM, PM must be equal to LO. PM must be equal to LO, but PM equals to 2. Here PM equals to 2, so from this equation 2 equals to PM equals to LO, we will derive that LO is also equals to 2 units. Here LO equals to 2 units. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we will get that side LP equals to side OM. LP equals to OM according to the same rule. So if we define LP as X, here LP equals to X, so from this equation X equals to LP equals to OM, we will derive that OM is also equals to X. Here OM equals to X. Okay? In the next step, we will focus on this point, that is the touching point between the circle and the quarter circle. So we define the touching point between the circle and the quarter circle as point K. Actually, at point K, the circle and the quarter circle have an internal lunge between them. That is to say, they are touching each other internally at point K. And whenever you have two circular shapes that have an internal lunge between them, then the straight line that joins their centers together must pass through their touching point. Okay, I'll repeat again. If you have two circular shapes that have an internal lunge between them, then the straight line that joins their centers together must pass through their touching point. In this case is point K. So here point O is the center of the quarter circle. Point O is the center of the quarter circle. Point K is the point on the quarter circle itself. So this is exactly the definition of a radius. That is to say, OK is the radius of this quarter circle. But before that, okay, so here, point O is the center of the quarter circle. Point P is the center of the circle. And the straight line that joins the two centers together is OP. And according to the rule that I mentioned, that straight line OP must pass through the touching point, that is point K. Or in other words, you can say that OPK is one straight line. Okay, so I found out that OPK is one straight line, or in other words, we can also say that points O, P and K, they are all located on the same straight line. Okay, so if OPK is a straight line, then OK is also a straight line. And here, point O is the center of the quarter circle. Point K is the point on the quarter circle itself. So this is exactly the definition of a radius. That is to say, OK is the radius of the quarter circle that is equal to capital R according to our definition. So OK equals to capital R. Here, point P is the center of the circle. Point K is the point of the circle itself. Therefore, PK is the radius of this circle that is also equal to 2 units. So in conclusion, found out that OK equals to capital R and PK equals to 2 units. Then, what is the value of line segment OP? From the drawing, it is very easy to see that OP equals to OK minus PK. Again, OP equals to OK minus PK. Repeat again, OP equals to OK minus PK. OK equals to capital R, it is the radius of the quarter circle, minus PK. PK equals to 2 units, it is the radius of the circle. So in conclusion, we found out that OP equals to capital R minus 2. Here, OP equals to capital R minus 2. Then I copied the right triangle OPM in a new page and we implemented the Pythagoras theorem on this right triangle OPM. Okay, so this is the right triangle OPM that I copied from the original drawing. The hypotenuse OP equals to capital R minus 2. PM is the radius of the circle that is equal to 2 units. And OM equals to X. So we implemented the Pythagoras theorem on this triangle OPM. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the surface of the perpendicular. The hypotenuse is OP, so the square of the hypotenuse is OP square. And it must be equal to the sum of the surface of the perpendiculars. That is to say, it must be equal to PM square plus OM square. So OP is capital R minus 2, therefore OP square is capital R minus 2 square, and it is equal to PM square. PM is 2, so PM square is 2 square, that is 4, plus OM square. OM is X, so OM square is X square, so in conclusion we found out that according to equation number 1, R minus 2 square equals to 4 plus X square. Here we open the brackets on this side of equation number 1, and we found out that R minus 2 square equals to R square, plus 2 squared, that is 4, minus 2 times R times 2, that is minus 4R. Okay, and it is equal to 4 plus X squared. Here we have 4 on both sides of the equation, so 4 will get cancelled. And we found out that according to equation number 1, x squared equals to r squared minus 4r. Okay, so in the next step, we focus at this point, that is the touching point between the circle and the semicircle, and we define this point as point T. So point T is the touching point between the circle and the semicircle. That is to say, at point T, the circle and the semicircle have an external notch between them. That is to say, they are touching each other externally at point T. Okay, and whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point. Repeat again, if you have two circular shapes with an external notch between them, then the straight line that joins their centers together must pass through their touching point. In this case, it is point T. So here, point P is the center of the circle. Point Q is the center of the semicircle, and the straight line that joins their centers together is QP. And according to the rule that I mentioned, the straight line QP that joins their centers together must pass through their touching point, that is to say, from point T. So if the straight line QP must pass through point T, it means that QTP is one straight line. Okay, so again, write down that QTP is one straight line, or you can also say that points Q, T, and P, they are all located on the same straight line. Okay, so if QTP is a straight line, then QP is also a straight line. And what is the length of the straight line QP? So QP is a straight line. The length of the straight line QP is QT plus TP. I repeat again, QP equals to QT plus TP. And here, point Q is the center of the semicircle, point T is the point on the semicircle itself, therefore QT is the radius of this semicircle, that is equal to 2 units. Likewise, here point P is the center of the circle, point T is the point on the circle itself. Therefore, PT is the radius of this circle, that is also equal to 2 units. So in conclusion, I found out that QT equals to 2 units and TP also equals to 2 units. So here, QT equals to TP plus TP, so QT is 2 and TP is also 2. So therefore, QP will be equal to 2 plus 2, that is 4. So in conclusion, we found out that the straight line QP equals to 4 units. Then we found out the value of line segment AQ. Point Q is the center of the semicircle. Point A is the point on the semicircle itself. That is to say, QA here is the radius of this semicircle, that is equal to 2 units. Okay, then so QA equals to 2 units. And what is the length of QL? The length of line segment QL, it is very easy to see from the drawing that QL equals to AO, that is the radius of the quarter circle, minus AQ minus LO. I'll repeat again, QL equals to AO, that is the radius of the quarter circle, minus AQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. Okay? So AO equals to capital R, the radius of the quarter circle, AQ equals to 2 units, this is the radius of the semicircle, and LO equals to 2 units. So in conclusion, I found out that QL equals to capital R minus 2 minus 2. Minus 2 minus 2 is minus 4. So in conclusion, I found out that QL equals to capital R minus 4. Okay, equals to capital R minus 4. Here QL equals to capital R minus 4. So in the next step, I copied the right triangle QLP in a new page, and we implemented the Pythagoras theorem on this right triangle QLP. Okay, this is the right triangle QLP that I copied from the original drawing. We just right now found out that QL equals to capital R minus 4. We have already found out that QP equals to 4 units. Here, QP, the hypotenuse QP equals to 4 units. And LP equals to X. So implemented the Pythagoras theorem on this right triangle QLP. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is QP, therefore the square of the hypotenuse is QP squared. it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to QL square plus LP square. So QP equals to 4, therefore QP square is 4 squared, that is 16, and it is equal to QL square. QL equals to capital R minus 4, so therefore QL square will be equal to capital R minus 4 square plus LP square. LP equals to X, so LP square equals to X square. So in conclusion, according to equation number 2, we found out that 16 equals to capital R minus 4 square plus X square. We open the brackets on this side of equation number 2, and found out that 16 equals to capital R minus 4 square. Capital R minus 4 square equals to capital R square, that is R square, plus 4 square, that is 16, minus 2 times R times 4, that is minus 8R, plus X square. So here we have 16 on both sides of the equation, so 16 will get cancelled. What is left from equation number 2 after we cancelled 16? In this side, nothing is left, we have 0. And on the other side, we have R square minus 8R plus X square. Here we added 8R to this equation, equation number 2, and found out that 0 plus 8R is 8R. That is equal to R square plus X square. Here we subtracted R square from this equation, equation number 2, and found out that X square equals to 8R minus R square. So according to equation number 2, X square equals to 8R minus R square, while according to equation number 1, X square equals to R square minus 4R. So we have two different expressions for X square. Therefore, we created the third equation that states that X square according to equation number 1 must be equal to X square according to equation number 2. X square according to equation number 1 is R square minus 4R, and it must be equal to X square according to equation number 2, that is equal to 8R minus R square. So here we added R square from this equation to this equation, equation number 3. And we found out that R square plus R square is 2R square minus 4R, that is equal to 8R. Okay, so here we added 4R to this equation, equation number 3, and we found out that 2R square minus 4R plus 4R is 0, and it is equal to 8R plus 4R is 12R. So in conclusion, we found out that according to equation number 3, 2R square equals to 12R. Here we divided this equation, equation number 3 by 2, and found out that 2R square over 2 is R square, and 12R over 2 is 6R. So in conclusion, we found out that according to equation number 3, R square equals to 6R. Here we subtracted 6R from this equation, equation number 3, and found out that according to equation number 3, R square minus 6R equals to 0. Okay, here we took R as a common factor out of those two expressions. So R is a common factor. What is left from R square after we took from it R as a common factor? What is left is actually R. And what is left from minus 6R after we took from it R as a common factor? What is left is actually minus 6. So in conclusion, we found out that according to equation number 3, R times R minus 6 equals to 0. So here we will have two solutions that are possible for R. Either R equals to 0 or R minus 6 equals to 0. But R can never be equal to 0. Why? Because R is the radius of the quarter circle, that it must be a positive number. It can never be equal to 0. So we cancel this solution, and we're left only with the second solution, that R minus 6 equals to 0. Here we added 6 to this equation and found out that R, the radius of the quarter circle, equals to 6 units. Therefore, the area of the quarter circle will be equal to the area of the circle over 4, that is pi r square over 4. And what is the area? What is the value of the shaded area? The value of the shaded area will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Repeat again. The value of the shaded area will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. We have already found out that the area of the quarter circle equals to pi r square over 4 minus the area of the circle is the area of the circle equals to pi r square, and r equals to 2, so it is pi 2 square. minus the area of the semicircle equals to the area of the circle over 2. The area of the circle is pi r squared, and the area of the semicircle will be equal to pi r squared over 2, and r equals to 2, so the area of the semicircle will be equal to pi 2 squared over 2. Here r equals to 6 units, it is the area of the quarter circle, therefore r squared is 6 squared, that is 36. In total, the value of this expression equals to 36 pi over 4, that is the area of the quarter circle, minus pi 2 squared. 2 squared is 4, and 4 times 5 is 4 pi, that is the area of the circle, minus the area of the semicircle, that is pi 2 squared over 2. 2 squared is 4, and 4 over 2 is 2. 2 times pi is 2 pi. So in conclusion, the area of the semicircle is 2 pi. So here 36 over 4 is 9, so in total this expression equals to 9 pi. So here we got that 9 pi minus 4 pi minus 2 pi equals to the value of the shaded area. 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, for note that the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. I repeat again, the value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, thank you very much.